Hello everyone, it's a real pleasure to be here. So let me start, and I hope to have a few minutes at the end for the questions. So who am I? I wear multiple hats. I'm a ECS faculty since 2020, actually arrived in the spring of 2021 here. I'm also director of the RISE Lab. I'm going to say a little bit about that. And one of the reasons I'm going to talk a little bit about RISE Lab is that a few companies I've been involved with actually are the result of the research we've done in these kind of labs. I also been involved in several open source projects and also have I have started a few companies. So let me start with the RISE Lab. So the RISE Lab, it's a lab which studies the design of real-time intelligent, secure and explainable systems and algorithms. So what we mean by that is that real-time means things about designing systems which are able to respond in seconds, even milliseconds. Intelligent, we mean systems which take decision based on sophisticated algorithms and models, machine learning models. Secure means systems which take the decision while preserving the user privacy and protecting the data and system integrity. And explainable means systems which make decisions which are auditable and verifiable. And this is an interdisciplinary lab. It's a holistic effort involving people from faculty and students across AI, security, hardware, and systems, and is supported by National Science Foundation and by many companies, some of them sponsoring this event. And they are great collaborators. So it's a very tight collaboration and interaction with the industry. So in addition, I've been, I mentioned, have developed a few open source projects, and these are a few of them. And Apache Mesos, which was a precursor of Kubernetes, Apache Spark, Alucio, and more recently Ray. And also I've been fortunate to be a part of a few startups, probably in particular many of you know about Databricks. And Databricks was, we started Databricks to commercialize Apache Spark, which Apache Spark was developed mostly in the lab previous to the RISE Lab, which was called AMP Lab. And Anyscale we founded this company 2 years ago to commercialize Ray, another system I'm going to talk about. So mostly I'm going to talk about here about this open source system Ray and Databricks. So what is a big trend out there, So well, really today every organization, in every shape or form, what they want to do is to collect more and more data, and they do so because they want to get some value out of the data. They want to get insights to improve their business processes, to improve their products, or even build the products based on this, making decisions on this data. And everything from recommendation systems and many other applications in manufacturing and healthcare and so forth. So how do you get data? How do you get value from the data? So you start from the data, and data again can come in different shapes and forms, different storages, different formats, and you ingest this data, and you do some reprocessing. You clean up the data, you do some ETL, extract, transform, load, and to put, to add some formatting to make it easier to analyze and to query. This is done mostly by data engineers. And then once you have this data which is more curated, which is more kind of in more standard format, stable format, maybe stored in a data warehouse, then they have data scientists and data analysts analyzing the data, trying to make sense of the data, trying to derive insights. Then you have to the next level. Once you get kind of the insights, you start to develop models, whether they are deep learning or classic models, statistical models like random forest, to make inferences and maybe decision on the data. This is done by machine learning engineers and data scientists. And finally, you are going to productize it. You are going to deploy it to improve your recommendations, to improve your decisions, and to embed in your application, hosted applications. This is software developers, machine learning engineers, and DevOps, which are in charge with taking care of the deployment. And really, the main point here is the application are increasingly incorporating AI. In all the industries, financial applications, transportation, manufacturing, and hotelier industry, hospitality, and many more. So now when you are starting to build these kind of end-to-end applications to get value out of this data, these companies are confronted with the following three challenges in general. One is about scale. The second is fragmentations. It's actually, you have different systems, and to build your end-to-end pipelines, you need to stitch them together. It's complicated, which makes the entire solution complex. So let me tell you a little bit about scale, and actually I'm going to spend quite a bit of time on this. So data doubles basically every 3 years, right? At least according to this graph, okay? So it's growing quite fast. However, this is nothing when you compare with the growth of the requirements, for instance, to train of the state-of-the-art machine learning models. And this plot shows on the x-axis the time. This is OpenAI plot. It's famous by now. It was released actually in 2019. So from 2012 to 2019, and on the y-axis is the computation, the compute required to train the state-of-the-art model. This is a log scale, right? So line means exponential growth. And according to this plot, the amount of computation required to train state-of-the-art models grew 35 times every 18 months. And what happened after that? Here I put in another data point, the GPT-3, which was released in 2020. And as you can see, there are no signs of slowing down, at least at this point. And this is not only for kind of esoteric application, like just playing games or things like that. Or it's also for real practical application, natural language processing and image processing. Okay. The same is true about the memory required to actually store these models. On the y-axis, you have the amount, the number of parameters of these models, which translate into how much memory you need to store and train these models. And again, on the x-axis now you have the time since 2016. And if you look here, and by the way, the last data point, which is BioDAO, which is the largest model to date, it's China. It's Beijing Artificial Intelligence Academy, or Academy of Artificial Intelligence. And it has 1.75 trillion parameters, okay? And that's a data point there on the top right. So if you look again, and the growth since 2016, so over the past 5 years, was 40 times every 18 months. And if you look, again, this is maybe too little of time interval to get some meaningful trend, but still, if you look only at the past 3 years, it's 340 times every 18 months. So why is this every 18 months? I put there because of the Moore's law. And Moore's law is ending. Right? If you remember in the heydays, right, in this the green region, the Moore's law improves the computer performance, the processor performance, one core performance, it was doubling every 18 months. So right now, however, this is no longer the case. It's like it's just growing a few percent every year. So now if you overlay this kind of trend, so now the red curve is the demand, computation demand. And this is the supply, so to speak. The Moore's law, this is 2 times every 18 months, right? And here, it's actually growth of the CPU performance, right? It's lower than the Moore's law because the Moore's law ended. Doesn't matter though. It's like the gap between these two curves is huge. Actually, even if the Moore's law would have continued, the gap would have been still huge between the demands and the capabilities of a single core. Of course, today you hear a lot of things about specialized hardware, right? People try to close the gap, coming up with new accelerators or improving the existing ones, like GPUs and from NVIDIA, TensorFlow processing units, Cerebras, startups, and so forth. Well, if you put those on the same plot, this is the GPU, NVIDIA GPU, and this is Google GPUs, they are obviously helping. They have much better performance than single CPUs. However, the growth is still pretty much roughly as the Moore's law, and the reason you grow because there are innovation in the architecture every generation. But the gap is still growing very fast, right? So you have two exponential functions with different exponents. The difference is still growing, different into 2 is still growing exponentially, right? And the same is true about memory. This is the GPU memory increased over, again, the last 5 years. It's only 1.7 every 18 months. So it used to be the case just 4 years ago that the largest models were fitting on a single GPU. Today, just to fit the model, you may require, the largest model today may require hundreds or thousands of GPUs. So really there is no way to support these new workloads but to distribute this application. So we have a really big scaling problem. And it's again, there are many ways to address the scaling problem, build, because it's such a huge problem, build accelerators, improve the algorithms, but it turns out, but it also it seems that you also need to scale to distribute these workloads. You can no longer run it on a single machine. So given that, let's look at today's machine learning ecosystem. Today's machine learning ecosystem is fragmented. Now, there are many kind of niche workloads in machine learning. First is, if you think about this, data pre-processing, featurization. You get some data, you need to extract the feature out of it, right? And all of these have to be scalable. So they need to run on multiple machines, so it has to be a different system. And what you are going to have today, you have different frameworks, different systems for each of these kind of workloads. This is true for featurization, streaming. In some cases, you have streaming data you need to process as soon as it arrives because you want to make decisions kind of more in real time, like financial industry. Then you need training and simulations. For instance, if you do reinforcement learning, you need simulations. And then this high parameter tuning, right? Once you have a model, you want to tune the model, changing the parameters. And then serving, you want to serve the model. So for each of these, there are systems today and there are scalable systems. The problems, they are different. And this makes building an application very complex because you need to stitch together this hodgepodge of libraries, systems, right? Which is hard, makes the application hard to build because you need to consider different APIs. So each of these kind of systems has a different APIs, right? And then it's hard to deploy because you need to manage different distributed systems. And it's also slow because you need to move the data between the systems. And when you move the data, you need to store the data, you need to read the data for some kind of storage. And that's kind of slow. Much slower than if you move the data in memory. So this is the goal of Ray, is to try to address this challenge, to unify the machine learning ecosystem. And the way this is doing is with Ray, this universal framework for distributed computing, and now to support the different workloads, instead of having different systems, you have just libraries on top of it. And here are a bunch of libraries which are already on top of Ray, and RLib is the most popular scalable reinforcement learning library. Tune is the most popular high parameter tuning library with scaling and many others. Okay? So the promise here is that you can build one of this end-to-end application from when the data is ingested until you make decisions on the data on the same platform, which is much simpler. And here are some testimonies for some users which are using Ray and using for some time in the industry. This is Ample, probably the largest fintech company. And they build the entire stack on top of Ray. Everything, Ray is like basic, you use Ray for streaming, serving, so basic workloads. And they use, on top of that, they build the libraries of algorithms, and then on top of that, services and applications like recommendation systems, like fraud detection, and things like that. And they use this in, Double 11. As you know, Double 11 is the largest shopping day in history. And this is also one of their quote is like, we build streaming, serving, and iterative calculation based on Ray, and also successfully in production. But you see, you build all of these kind of workloads. You should support all of these workloads on top of Ray, a single system. This is another example from Uber. Uber was one of the pioneers building these machine learning platforms. With Michelangelo, they released open source some time ago. Some of you may know about it. The second version of machine learning platform they are building now is on top of Ray. And this is what they say, by leveraging Ray, we can combine the pre-processing, distributed training, and high parameter search, all within a single job running a single training script. So it's like this provides an environment which is no longer fragmented and makes building the application much easier. This is it's a nice, another example. This is the winning boat who won this sailing competition, America's Cup. America's Cup is the most prestigious sailing competition, dating from 1841. It happens once 3 or 4 years. And it's a New Zealand boat. And it was designed with the help of Quantum Black, which is a McKinsey company. And they use Ray and RLib both to design the boat and to train the crew. Okay, what else can I say? This is, it's very popular today. And this is a GitHub star. It's one of the metrics people use to assess the popularity and the adoption of these systems. And this is compared not with single node libraries, but with other distributed systems, right? And you can see here, maybe you may have this Spark is up there, Ray, and then Kafka, Flink, Kubeflow, and so forth. So as you can see, it's very fast growth. Actually, the fastest growing here are Ray and Spark. Okay. So now I'm going to switch gears and talk a little bit about Databricks. So Ray is trying to focus really on scaling machine learning applications. But it's not doing much about the data. Data is just ingesting the data and so forth. But we discussed that we need to take the data, to clean it up, to pre-process the data and so forth, to do it end to end. And Spark is actually, when we designed Spark, it was a system to scale up data processing. And now it's probably the de facto standard to do so with open source project. And we started in 2009, the project in 2010 was open source. Databricks started it in 2013. And Databricks is providing platforms on multiple clouds, or running on multiple clouds to help users to unify the data and AI. And it's one of the fastest growing enterprises companies. It today has 2,500 employees. And this again, you don't need to look at the details here, but really this is how, if you need the data processing looks today, right? It's very complicated, even talking about data processing. You are going to process on the raw data and so forth images. It's a different one workflow. You want to have an analyst to query the data using SQL. It's a different flow. You want to, do ETL, extract, transform, load. It's a different workflow. This is what it tells you, right? So everyone, data engineer, data scientist, and so forth, data analyst, they have each of them a different workflow, and each of them is very complicated again to combine them. And more and more, you do have the data in this kind of data lakes, like S3, but still on top of that, it's very complicated. So Databricks is again similarly unifies it. So basically, you have a single layer to access the data and support these different modalities for data scientists, data engineers, machine learning engineers, and so forth. And it's engineering from ground up, right? So basically, one way to do it, you can provide access to the data both to SQL, right, to analysts using SQL, like data warehouse, and then also to machine learning. You can use it for image processing and things like that. So all of them, the same storage, the same interface. Well, today you have different. You have a data warehouse, even like snowflakes. You cannot use it effectively for machine learning because they are different workloads. So this is about, this is about, showing some, some screen, basically unifying the machine learning and data science workflows, right? This is about showing also in the same environment. You can have, data engineering can enable data engineers to build pipelines to transform the data, to process the data. This is analytics workload. This is about enabling data analysts to use SQL to access the data, right? So I'm not, and I'm not going to explain all of, everything what happens here under the hood. Hopefully I just give you a high-level idea. And instead, let me summarize. So today, every organization wants to get value out of the data and AI. There is no question about that. However, this is hard because scale, complexity, and fragmentation. Actually, there are Gartner's reports which basically say that for AI, 85% of the project fail. Okay? It's just too hard, or maybe you don't have good data or anything. 85%. So that means huge challenge still. But the big challenges also comes opportunities. And this is for you to say these opportunities. Thank you.
Bună ziua, mulțumesc mult pentru prezentare. So we're so inspiring for a generation of women in development. Thank you so much. My question was about public opportunities, and you talked so much about the private companies, and I was wondering.
Yes, so that's the difficulties here. Let me just come closer.
So I was wondering about the public opportunities with their public services, as for example government, for AI, and maybe the challenges they face with AI and like the public space.
So the question is about the opportunities in the context of, to elaborate on that.
Yes, on the public, yeah.
Okay, so let me elaborate a little bit more on the opportunities. I think that with each of those, there is an opportunity. Like for instance, scaling. I think scaling is like you saw the demands grow extremely fast. And closing this gap, you can do through software, hardware, and better algorithms, right? So in any of these directions, you can see, like, for instance, you have, for instance, a hardware. You have a renaissance now of hardware companies coming up with new chips to close that gap. And, like I mentioned, Cerebrus. And even every cloud today, they start building their own chips, not only Google, TensorFlow processing unit, right? Then you have, for all of these things about, like for training and so forth, new algorithms which are more efficient at scale, distributed like Python, Lightning, and things like that. And obviously the algorithms, again, many smart people are thinking to improving the algorithms. Compressing the network, you train a big network, then you compress it when you are going to serve. That's one. I think that complexity and fragmentation is a little bit harder. You need to understand, like, it's also the fact, like, you need to look about why this project fails, like I mentioned, failed. And there are many reasons. One, maybe you don't have good enough data. Like, you hope that you have enough data, you have the data for a particular application, but it turns out that you don't have that data. And it can be the case because, and now is more and more regulatory constraints, and with privacy constraints, privacy regulations, like GDPR or the CCPA, California Consumer Privacy Act. There is a challenge there. There is another project I didn't mention, it was opaque. So then another challenge there is that how you can still extract value out of the data in the presence of regulations, more and more regulations. And there's the idea there are algorithms which can process confidential data without revealing the data to the person who is processing it. Right, that's another direction. And a lot of things about complexity deals with the fact that you have interesting models being developed by data scientists, moving them in production. Moving them, and then this is called ML ops. So, and moving them in productions is about, you need to look at the model drift. The data distribution changes. The model which was perfect yesterday is no longer working well. Detecting that, retraining it. These are all very hard problems. And then it's everything about explainability, bias, eliminating the bias, and things like that. It's a lot of problems to overcome. But the main point is the future. Just extract value and use the data to improve the business of every company wants to do that.
Yeah. Due to time constraint, we will allow one more question.
So, okay. Sorry. When it comes to like scaling and complexity and fragmentation, right? So, I mean, what I was thinking is, for example, when it comes to like different kinds of data, like for example, if there's an inventory management robot or something that's providing real-time feedback or any kind of data for that example, how do you? Sorry. How do you take all this data and make these processes more simple and incorporate them within a larger company?
How do I make all
these processes more simple? Is that what your company, is that the framework behind it?
How do I make all the processes
like simple and streamlined?
Oh, simple.
Streamlined.
Streamlined.
Yes.
And you are talking about particularly about what I said about Ray earlier on, or?
Yeah, that's exactly what I'm asking. So like, what I'm asking is that what's going on? Like, are you taking I don't know if this seems silly, but are you taking all of these processes or the software and basically streamlining all of it so it's simple and creating a workflow?
Yeah, so here is what you want to provide, ideally, and this is what I try to provide. You want to provide for the developer the illusion of an infinite laptop. What this means is that a developer should have the same kind of experience developing programs on their laptop. But now imagine, you want to preserve that experience, that workflow. But now imagine that that laptop has infinite resources. Okay? So that's kind of what you start with this. Now, how do you do it? It's complicated, right? It has to, you start to what kind of, how you are going to extend or what kind of API you are going to show to the programmer, right? So that you have a chance under the hood to optimize things. You need to manage the nodes. You need to auto-scale. You can start with one node, and as the demands of the workload increases, you start to allocate more and more nodes, right? Then you need obviously to care about performance communication between the nodes. So yeah, you can look at one of these papers, but it's a little bit of everything. It's in order to provide simplicity in many cases, what is under the hood is quite complex.